All right, on with explanatory data analysis. The term as such, I think, is already quite telling, right? What I put here on my intro slide is getting a first look at the data. And this really is what EDA is about. We are always in the setting, or we always consider the setting, where we will use some analytical models eventually, and then trying what type of variables a data set entails, what they might mean, how they might be relayed to a target, if any. That's pretty much the scope of EDA. And you see all these slides, you see all these plots on the slide here. Many of the charts you already know well. It's very much about analyzing the data in visual means. We will delineate that a bit more formally shortly, and using a set of techniques from traditional statistical multivariate analysis, multivariate statistics. These type of techniques play a major role here. And I just wanted to highlight that more recently there is another term that is sometimes coming up, the term of visual analytics. It's yet another member of the analytics family, really, where there is some overlap, in my opinion, in that these type of techniques, these visual, graphical approaches to analyze data, to understand data and what it tells, they also play a key role in what nowadays is sometimes referred to as visual analytics. The focus there, however, just to delineate this briefly, the focus in visual analytics is more to use these visual helpers in order to inform decision making, possibly without the use of more sophisticated models, without the use of more sophisticated algorithms, like we will focus on in this course. Anyways, let's move on here. So we got a data set, we're trying to understand what is in there, and this is the focus of EDA. It can, well, basically be associated with Tuckey's pioneering work, which was carried out in the 1960s, famous statistician. And originally, EDA was basically an exercise that helped to formulate hypotheses for research. Hypotheses how data might behave or how real-world phenomena might function that have been observed through the lens of capturing some data. Or for model selection, EDA is useful. If you use a linear regression model, you know how this is built upon certain assumptions, normality, etc., right? Linearity, additivity. And EDA might provide a vehicle in order to verify whether these assumptions of some statistical technique are actually plausible. It might also help us with finding some structure, like dependency or co-occurrences in the data, which could inform subsequent step in analytical modeling, feature engineering, for example. And also, lastly, it's a highly useful technique in order to identify data issues, mistakes, errors, missing values, etc. I put this table here and deliberately left it empty in order to structure our thinking a little bit. When we talk about tools to do EDA, to do explanatory data analysis and peek into a data set, we could distinguish them. For example, along the row category here, are we talking about graphical tools, like this nice chart you saw on the previous slide, or are we talking about non-graphical tools like statistics? And either case, we can also distinguish whether we are interested in an individual variable or an individual column in our data set, it's univariate, or whether we are interested in dependency structure that typically occurs across variables, between two or even more variables. That's a multivariate setting. And just to emphasize the meaning of these small, humble taxonomy, we could try to populate this table with some examples. So if we look for a technique that looks at an individual variable and is a graphical technique, ask yourself what might be an example for that. And well, since we are not together today, I don't want to wait too long. An example for a graphical univariate EDA method could be, for example, a box plot. Well, just in the unlikely, in the unlikely case that you haven't heard about a box plot, we're going to look at that in more detail. It's a very popular type of graphical tool to understand the distribution of individual variables. And of course, so is the histogram. Again, more insight on these shortly. And now, what about non-graphical techniques? What would be a non-graphical equivalent to these? And well, that should not be too difficult. You learned about statistical moments in your undergraduates. So something like the mean as a way to identify the central point of the distribution of one of the variables clearly would fit. So with the second moment, let's put the variance here. But mean variance, that is defined for numeric variables only. Previously we distinguished continuous and categorical variables, so something like the mode. I'd also put to learn something about a nominal variable, for example. Okay, and now let's move on to the multivariate setting. In terms of graphical tools, typically you would analyze bivariate relationships between two variables. If you use graphical tools, more than two, often becomes a bit hard in terms of visualizing, although there are very powerful techniques out there these days. But let's put a scatter plot, just to have one example. So simple scatter plot, very nice tool to understand whether there is dependency between two variables, or two numeric variables to be precise, or whether there is not. And then, well, a non-graphical equivalent to the scatter plot, guess what's coming? Of course, right? Correlation. That's something we could put. That is a measure of the linear association between two variables. And in that regard, it perfectly fits in here. There are multiple types of correlation coefficients that we could distinguish here: Pearson, Kendall, Spearman, etc. Can look at the whole covariance matrix. That's basically the type of tools we could basically fit in here. But let's look at some of these examples more closely, starting with the histogram plot. I put a histogram here of some hypothetical variable age, which again might pop up in a credit risk dataset, marketing dataset, any type of dataset where we look into customers, or an HR dataset as well. And here we have the empirical distribution of our variable age. It's univariate. We see age and that's it. At least this version of the histogram. And you see how it is a useful tool to understand the distribution. And it's also a useful tool how to identify certain anomalies, let's say. Age values between 0 and 5, that's very suspicious. Also, if we look at the upper bound here, 70 to 200, quite likely that there are some errors in our data set, some age values that were incorrectly recorded. And also, we immediately see where the majority of our client lives, in which age range we see the majority of the clients. Okay, now you will have seen, or well, the experts of you already have noticed that this is not a proper histogram plot. Here it's just a bar chart of the empirical frequency. So bear with me for being slightly sloppy here. But you got the idea how we can basically look at the empirical frequency of groups of observations in order to understand how a variable such as age distributes. And that is a popular tool for univariate explanatory data analysis. It's super useful. In real world settings, you will often see also this long tail where you have the mass of the observations in some part, and then a few observations and fewer observations with larger and larger values of your variables. And as a matter of fact, this distribution, which is really characteristic of many variables that we see in real-world data sets, this long tail, it might already signal that this variable could benefit from some preparation, some transformation before we put it into an analytical model. Intuitively, if you think about a linear model, it might just not be the best choice here if you have this long tail distribution. Okay, to be fair, we cannot really make the case from this univariate analysis, but if there are some large values, some observations in our data with large age values, as we see here, and we fit a line to the data and trying to understand how age and some target variable relate to one another, I'm not sure a linear model is the best way here. It might be affected by the outliers pretty much. So seeing a distribution like that, we might want to investigate whether addressing the outliers in our data set is useful to help our analytical model, provided that there were something like a simple linear regression model. Well, more on outliers shortly in the subsequent part. Let's look at another version. This is a stacked histogram, and I copied that pictures from Wilke 2019. I strongly encourage you to check this out. If you go to the very end of my slide book, you'll see the references, the literature information for all the references here. This is actually a blog, and one of the many great blogs, in my opinion, on analytics and data science. It's all about visualization. So in addition to the graph, you also have some nice codes there, how to produce these graphs. It's also about age values and empirical frequency. You have these counts here. And he's using the Titanic data set. It's a famous data set that's often used in education and occasionally in papers as well. So it's about passengers that traveled, were unfortunate enough to travel on the Titanic, and we see their age distribution, and we see how this distributes across males and females. And it's called a stacked histogram that we see here, and the use case is to visualize multiple distributions in one graph. That's the grouping here into males and females. And well, we see these plots, we immediately understand them. A point that I would like to make here, in the blog post, this chart is actually highlighted as a bad example. So it's not liked by Wilke, and he has good reason, and I agree with these. You might just accept the visualization, but verify for yourself. To which extent are you able to answer simple questions such as how many female travelers on the Titanic were 20 years old? That's a very simple question, isn't it? Or 30 years old. And if you try to answer that, let's assume here we have this is the relevant bar, right? So here we have the 20, that's the 20-year bar. And now, well, so let's say we are clever, so it's called a stacked histogram. we don't ignore this term. So the bars are stacked on top of each other. Okay, if that is the case, then right, we need to find basically, we need to go here, finding this age corresponding to that. So maybe that's 50, and then this, let's say that's 78, right? Let's assume that it's probably not 78, but anyway. So then we have the range, and if we assume, so that's about 50. So we have the range here, which obviously is 28. So okay, but it's stacked upon one another, right? So we will need to project that down, and then the orange line, if we're not stacking it, so it should be here, right? 28. Well, might that be maybe here? So here we find the females, and then okay, yeah. So you're getting my point. It's a popular and truly useful type of graph, but it blurs some important matters, as I was trying to exemplify here, that some obvious questions are not so easy to be answered from this type of analysis. And this is why it makes a lot of sense to really look more deeply into the scope of visualization techniques, and there is a lot more available than what is covered in standard textbooks and standard lectures as well, I believe. Same with me. But thanks to Willeke, I have at least some examples here. So look at this one. It's just the same data, and we made a minor change to our stacked histogram. And now we can discuss, is that any better? And my answer to that would be yes. We again have males and females in blue and in orange. We have the average age values, note these here right now, on the ordinate. And we have the counts on the abscissa. And it's because of the way we present the data, it's now a lot easier to come up with the same answer for our questions, like what's the how many of the females were aged 20. So we see that right here. There it is. Here's our 20. So here's the age of 20. I shouldn't use the orange, really. Sorry about that. Let's take a red one. So here's our 20. So let's check. Okay, here's our bar. And there is the bar. And oh yeah, well, if you're a bit mild with me, let's say that also translates into something like 28. But we see that a lot easier, I would argue, than we did before. Also, differences in the age distribution are easier to spot, differences between males and females. So by just making this minor adjustment to the standard histogram plot, or the stacked, I should say, if we're interested in two groups and analyzing their distribution, then this, in my opinion, would be a better visualization. It's maybe not perfect though. Let's see what can be done on top of that. Here's another example, and by now you will know it's the same type of data. Very nice one. Here we see the whole distribution. We moved beyond the histogram and use some density estimation technique here, kernel smoothing we typically use to create visualization of the density of age values, and we get that from males and females. And the gray shaded area, they give the overall distribution. So let's convince ourselves how this produces yet some additional insights into the data, or maybe not additional, but some insight that are easier to realize. I would say that, first of all, this is the first visualization of the data where it is immediately clear that the number of males on the Titanic was apparently a lot larger than the number of females. And we can easily obtain this insight by comparing the distributions, the gender-wise distribution, to the total. We also able to spot some artifacts in the distribution, maybe a bit more easily. Well, consider this little bump here in the female distribution. Well, maybe it is just an artifact, but looking at the distribution, there are maybe more modes compared to the males. So to be fair, this additional insight we probably got from moving from the histogram to the density. But if we look at the total distribution, then you could maybe make the point that if we visualize our data in this way, we can also get some additional insight on the individual groups that we are interested in. So what's the take home here? Histogram plots, one of the go-to techniques when we talk about EDA. It's clearly useful, but in a strictly univariate setting, its value is maybe limited, and as soon as we move beyond the strictly univariate setting, we want to do some categorization here, looking at distributions across gender or other type of nominal variables. It's worth investigating what other techniques, what more sophisticated, if you wish, techniques exist to raise the insight that you get from your visualization into the data. And after all, getting a first look at the data to get some understanding how it behaves is the very purpose of EDA, right? Let's look at one other popular plot. That's my favorite one. It's super useful in EDA and data prep. It's the box plot, which probably you know, but just to be sure, if you're well familiar with the box plot, just click feed forward. No worries. For those who feel a bit shaky here, we are again depicting the distribution of an individual variable, which could be age. Could be age again. I didn't put a scale here. Bear with me. Maybe I should. In this way, the scale would be here. Let's say this is our scaling. Let's say it's age again. It could be something else, really. It doesn't really matter. And here we just have the individual age values, right? So this is how to read the box plot in the first place. And then we have some characteristic points that this box plot is meant to identify. We use a different color here. Why not using purple? My daughter loves purple, so let's go for purple. We have Q1. Here's Q1. Oh dear. Did I apologize for my drawing recently? I probably did. Well, but I can't do it often enough. Q1, the first quartile. Now draw on your expertise in statistics. It's a characteristic point of a distribution. It's the point, the age valued, which basically covers the first 25% of the data, meaning the 25% of observations of people in our data with the lowest age, the youngest ones, the 25% youngest people. That's actually the easiest way to refer to that, isn't it? And same with Q3. So here's Q3, right? Roughly. That's also an age value. And this age value, which obviously is a lot larger, would basically cover the 35. Sorry, did I just say 35? I think I did. The 75% of youngest people. And then this is a box. It is the boundaries of our box, and the box plot are exactly identified by these two characteristics points, the first and the third quartile. And then we also get an indication where's the median, which is just here, which is nothing but, well, the second quartile, if you wish. It's just that we don't refer to the second quartile as the second quartile, but rather refer to it as the median. But it's exactly the same thing. So here the median, it covers the 50% youngest customers or passengers or people in our data set. And then we also have these whiskers. that are these things here. Two of these. One I labeled min, one I labeled max. I'm going to relax that shortly. But for now, you could think of these as identifiers of the largest age in my data set and the minimum age of the data set. Normally there are not, but for now it's okay to think of them. And finally, the inter-quartile range, IQR, is another useful statistics. It's just the difference between Q3 and Q1. And this range here, the inter-quartile range, if you think about it, it covers the 50% middle of the data, the middle 50% of the data. And in that regard, it's a measure of the spread, how the data distributes and then varies around its central point. Yet it's a more robust measure of the spread compared to, for example, the variance or the standard deviation, because you just consider the middle 50%, and thereby you get rid of all the extreme values which would heavily impact statistics such as the variance, right? So this is why it's more robust. And the box plot, well, why is it so useful? It depicts the distribution of a variable. If you examine this example here, you will note that the distance in age between Q1 and the median is a lot less than that between the median and Q3, right? So obviously, it's a lot shorter than this distance here. So the age range distance, when I say distance, I mean age range, because this is really what we see here. It's the range in age, or whatever the variable is about. And then, what is it telling us? From Q1 to the median, from the median to Q3, it's always like covering 25% more people. So the number of people that go into these buckets, they are the same. But the degree to which age gets larger and larger when we move from Q1 to the medium is a lot less compared to moving from the medium to Q3. Well, in other words, in order to capture, once we are at the median, the next 25% of people with higher age, right, we need to consider a much larger range of age values compared to covering the next 25% from Q1 onwards, all the way up to the median. Which, well, in a nutshell, this only means that our distribution has exactly the shape that we saw earlier on in the histogram, i.e. this long tail, where then things get to level off. Right? So there are fewer and fewer people with larger and larger ages. That's pretty much what we see here from comparing the distance from Q1 to the median and from the median to Q3. And we see that from the box immediately. So that is useful. Common use case for the box plot also is to talk about outliers, or to identify outliers. Let's talk about outliers briefly. And this goes back again to Tuckey's seminal work. There he came up with a definition of what is an outlier. Intuitively, an outlier is an observation with a value that is so large that we consider it abnormal. So an age value so large that we would consider it non-normal. That is an outlier. But this is a fluffy definition of what an outlier is really. What is large? What is unnormal here? How large does it need to be? How old does somebody need to be, or how young, in order to count as an outlier? And obviously this depends on the setting. The range of age values that we saw among Titanic passengers will be a lot different from the range of age values that we would see in the age distribution of loan applicants for some financial institution. And the rule of Tuckey is that an outlier is a value so large or so small that it is more than 1.5 times the inter-quartile range apart from the boundaries of the box. So you see how I have the little blue blocks again, and you see Q3. Here's Q3, right? Q3. Oh, it's not really a 3. Well, maybe it's vaguely a 3. But now understanding the box plot perfectly, you know that this is Q3. And then we take the interquartile range and we add it up to Q3. But not only that, we first multiply it with 1.5. So that's basically this distance here, right? And I drew this using PowerPoint, right? So it's roughly 1.5. Bear with me. And any value that is above that threshold here, 1.5 times the interquartile range, this value we consider a mild or a soft outlier or upper outlier. The same story goes for soft lower outliers, i.e. values that we where if this is Q1 and then we go the same type of distance downward and find observations in an age range less than this cut point, then we consider it a soft lower outlier. And if we double the distance and have 3 times the interquartile range above or below, then we call these cases extreme outliers. And clearly this is a rule of thumb, but it's standard practice, and in fact you could also relate that if you wish to probabilities if you assume that the data that you analyze, your age distribution, for example, follows some statistical model. Here is an example where you can basically relate the box plot under the assumption of normality to the normal distribution, and then also basically relate the thresholds, 1.5 or 3 times the interquartile range, to probability areas. And that is a nice visualization that I also found online, and I invite you to check out the blog here of Karanik 2018. At least this is the date that was written there. And it reminds us simply of the fact that although we are not specifically looking into the full distribution and instead just characterize it or depict it by characteristic points, there certainly is a way to interpret the findings of the box plot in terms of probability, and how likely then a soft outlier is to occur if our data is normally distributed. And you see that here how we would obtain a probability of 0.35% of observing a soft lower outlier under the assumption of normality. Right? Now, what I wanted to note here as well is that this version of the plot, let me use red, is more common than the one I was showing you earlier. Here the viscous, so these little things here, right, the viscous, they are called, they actually do not identify the minimum and the maximum of the distribution, and rather they identify the threshold of the soft outliers, and then points beyond that are identified with a dot in the box plot. That's the version that you will typically see when you use software to analyze your data, or some derivative of that. On the left hand side, I'm showing you yet another type of box plot. Here we have notches, as they are called. The notches are meant to create a confidence interval around the median. So the 95% confidence interval around the median is highlighted by these notches. Many software packages will by default create the boxes in this way to convey more information, or at least they will offer you a parameter with which you can control your boxes, your box plot, to then add notches if you wish. And also an option would be to show the mean in addition to the median. Exemplifying this here with the red cross, that's my mean. The mean of this distribution might be a little bit above the median. So maybe we have some large, maybe even some very large observations which impact the mean more heavily than they impact the median, right? This really should make sense to you. And therefore, it is higher than the median. And this is also potentially useful information, and thus we could think of ways to add it to our box plot. And here you see how this can be accomplished. Last example, second to last example actually, from SAS. I took that. Till now we were elaborating on single box plot, which refers to a single variable, which there is nothing that prohibits presenting multiple box plots in one chart, and then the multiple boxes can either refer to different variables. We might need to scale the value ranges in order for that to make sense, or as shown here, the multiple boxes could equally refer to repeated measures of the same variable. Our example depicts sales, and we have sales data for all the individual months of a year. But of course, a month is a set of days, so across each day we observe a couple of individual level sales, and this daily sales value we visualize with the box plot. No whiskers here, no outliers, not to worry about. I talked about the different versions, how we can basically create a box plot. We have our medians, of course. Look for the white lines, horizontal white lines that cut the boxes. And in addition, we have the little diamonds in each of the plots. And looking at the header, so it's sales and mean sales, they say. You know what these diamonds are? They are ways to depict the mean of the distribution and its confidence interval, which is then so if the line basically identifies where the mean is, and again in this example, with my drawing that's a bit tiny here, maybe a little better. So if this is the mean, and we again observe the mean to be a bit above the median, then here basically we visualize a confidence interval around the mean, the estimate of the mean. Same idea as with the notches, just that this interval, this confidence interval, is constructed around the mean, whereby the notches are constructed, not typically, always constructed around the median, right? So again, useful visualization. We look at it, and once we familiarized ourselves with what the box plot is and these different versions of the box plot, we can really learn a lot about the distribution of sales values across the individual months of a year, or that year here. March, April, apparently the months where we are a bit stronger. We also note a little January effect here, where we don't do so well. We see a drop of sales in July, so that could give us an indication how much our sales are impacted by the summer holidays, for example. And well, we could now, with some background, some context, what type of product is it we talk about, what type of year is it we talk about, we could maybe create some nice narrative, what we see here in our data, by just looking at the individual box plots. Last example now, finally, violin plots, I'm trying to get a bit more exotic. If we were together today, I would probably ask how many of you have worked with violence plots before, and I would expect that this maybe not so many. I still see that as a slightly more exotic way of visualization, which of course is very useful again. So let's try to make some sense out of this plot. We have weekdays again, and the measure we look at is now called total bill. Total bill, okay. What is it we bill our customer? Well, maybe this is some kind of subscription service where we analyze how heavily the service is used by individual customers across different weekdays. That's something it could depict. And in its core, we find a box plot. You have to look a bit hard here, but yeah, that's meant to be kind of box plot, right? And you see how this makes sense. There is apparently a box in here. And from these boxes, we get the median, this time as a white diamond. We also get the inter-quartile range, and thereby we get the first and third quartile, although admittedly, in this example, in order to identify the corresponding values, what's actually the median or what's Q1, Q3, it's tough, right? So from here, going here, oh dear, that's a tough one. Not to mention about Saturday or Sunday, where we need to go all the way. Okay, Sunday is maybe easy because we have the median pretty much at 20, but for Saturday we need to go all that way. So that's quite hard to eyeball what the median of the total bill per Saturday on Saturdays might be, but you get the idea. Just that we have more than the box plot. We also have a density estimate, and this density estimate we can even stratify. It could be symmetric, so you will see versions of the violin plot where the right-hand side and the left-hand side of each individual box are just equivalent, where it's symmetric, which is the case when you don't group. But this is already the more complicated version where we can also group. For example, gender-wise, you have this gender grouping here, and you see how the total billing per weekday distributes in total. That you see from the box, but you also get information how it distributes across males and females. So this is really interesting, potentially, where maybe on a Thursday, arguably, the distribution is still different between males and females. It still differs, you see that easily, but relatively to a Sunday, let's say, Thursdays are more similar gender-wise. On Sundays, the behavior between males and female appears much different, but I need to tell you that in my interpretation, I'm actually referring to the size of the the groups, because the width of these violin, of the sides of our violin, that's probably a better way to refer to that, but you see what I mean. The width of these things, they signal frequency. So basically for Sunday we see, or the take home for Sunday is, okay, a lot more male customers than female customers. And that's something for Thursdays, it seems more similar. The actual distribution, and there I need to qualify that, going back to Thursday, which is the easiest one because leftmost, we also see how the central point of the distribution, of the billing distribution for females, let's clear up the plot a little bit, which is probably somewhere here. So we clearly see how that is less than that for males. So the average billing amount on Thursdays for a female customers will be less than that of a male customers. That is insight that we obtain. The long tail for females is also even more extreme, maybe to say, than it is for men. So numerous insights you can get from this visualization. Or let's think about Friday. For Friday and for females, there appears to be no really extreme case, right? So the distribution almost ends here and here. There is no long tail, really. So that is the pattern we see. And it's a non-trivial visualization for sure, but as I'm trying to exemplify here, you can take a lot out of that visualization. And this already is a fairly sophisticated way of analyzing your data, generating hypotheses. Right? We could formally test now the hypotheses that female customers spend less than male customers. Because we found insight or evidence that might be the case, and we could now formally test that evidence if we were aiming at some statistical testing here. These visualizations, they help to gain an understanding of the data, how it behaves. They will inform data preparation, but also they help us to generate these hypotheses, what might be mechanism. Well, I hope you believe and are able to convince yourself that in a real-world setting where this is your data, where this is your sales data, it will be really interesting and important to perform this analysis. So let's sum up. Explanatory data analysis, what are the take-homes? It should routinely be the first thing you do. Once you obtain a new data set, once you get your hands on a new data set, analyze the distribution of individual variables, look at the moments of the distribution, look at charts such as histograms, box plots, etc. Obviously, the charts are more insightful, but also, obviously, if the data that you obtain is high-dimensional, where you have hundreds or even thousands of variables, looking at a box plot of each of these variables is pretty much impossible. So there you would probably start with some non-graphical type of analysis to get a first intuition and try to single out those variables that are worth investigating more thoroughly, right? We learn about these perspectives, uni, multivariate, graphical, non-graphical. Well, I didn't really stress it, but it should be obvious that there is no silver bullet, there is no solution to EDA or no single go-to technique. Many useful technique, and you've seen these, and also learned about some, I wasn't sure how to refer to that really. I said non-standard ways, but that's clearly subjective. What's standard, what's not standard. Some would argue, oh, come on, violin plots, that's old stuff. We learned about it so long ago. Maybe others of you have seen it for the very first time, so that's a bit subjective here. Don't put too much attention to that. There are clearly newer and more powerful ways to depict data, more complex data, or to just get more insight from simple data. And I would invite you to check out the references that I gave that are very useful to deepen your understanding of these tools and to see some more examples. The pictures I put here are yet more examples of what I consider rich information, rich and sophisticated means of visualization. We have a mosaic plot on the lower left side. We have cohort charts and Sankey plots on the right hand side. All visualizations I borrowed from a paper of my colleague Alona Jarova. She was analyzing some really interesting data. I mean, for me it was really interesting because she was actually analyzing the research performance of professors of Humboldt University of Berlin. well, the analysis is not carried out at the individual professor level, but at the group level or faculty level for obvious reason. Clearly, this is highly sensitive data that she was able to analyze, and she wanted to, well, identify things like collaboration patterns. So, for example, the charts on the right-hand side are means to visualize. Look at the upper one. The chart diagram here. If you look closely, you'll see these abbreviations. EDU, that's education. Psy, that's psychology. Bio, agricultural sciences. Yellow is econ, that is us, right? This is us. It really is us, by the way. And she's visualizing how many papers are co-authored with colleagues from other faculties. So apparently, there is a strong link between us, the economists, and colleagues from the agricultural sciences. And indeed, that is true. They also make a lot of use of data science type of techniques, for example, and other sophisticated statistical techniques. They build a lot of empirical models, which somewhat explains this collaboration. And it was interesting insight to the management of the university, how these dependencies work. And well, if you are interested in these things, you see how I get really excited about this, because it's essentially it's our data, really. I invite you to read Alona's paper. It's a great read, great paper, and you find it the preprint on the Social Science Research Network. I cited also in the appendix. So have a look at that. But anyways, let's conclude this bit. EDA. You've seen some examples, and I know that you already played in the tutorial with some R code, which allows you to create some of these plots. Now you know what also is available, and I invite you to keep on reading and deepen your understanding there, because as said, remember the GGO principle. The more effort you put into the data preparation and the explanatory analysis of the data as part of that, better performance will you get in the end from your analytical model. So it's clearly a worthwhile endeavor here. All right, that is about it. Thanks for watching, and we will soon continue with our part on data preparation.